So we are talking about MIPS 6400, and specifically the very interesting thing about this processor is that it is meant for the intellectual jobs in a heterogeneous system where you have many cores and specialized video processing blocks. In each core, there is a multi-stream on a core, which I mean hardware support for the multi-stream. That is different from the software multi-threading. So the cores of this class are used in Mobileye company by Volvo, Tesla, BMW, and many other automobile companies for the driver assistance devices. And so to understand how to present, let me ask you, how many of you understand the microarchitectural principles and stall forwarding, all those things? I just want to understand, should I show you the software or oriented presentation or explain something? Yes, some of you know, but most do not. Most of you don't. So I shall use it as an opportunity to give you the basics about the processor conveyor. And you will understand the logic of the difference of microprocessor cores and how the market influences different processors merging into one. So at some moment, our company, yeah, the mouse. Yeah. At some moment, our company was sponsoring translation. It was supporting a Harris textbook on computer architecture that I do recommend to every programmer who want to understand some basics of the hardware. So languages of the hardware description. In particular, you can use the language Verilog to build your own processor. And here you also read what is a conveyor processor and the difference between the processors with different internal content organization. So at this diagram, you can understand the concept of the conveyor, of the pipeline in the processor. In the hardware, you have some simple principles. In the hardware, you have a signal of a frequency, and in the hardware, you can describe what is happening inside one round. So you have D triggers of flip-flop and stored in the processor, and through the language like VLOC, you describe what's happening within one round. And after that, a special software will turn this description into this picture, and then place and out happens to it. It will have several technological steps to give you a file, DGS2, that goes to the factory that builds a processor. In this description, you can, for instance, arrange that a command would be done within one cycle. But in this case, this cycle will be long. And in this case, the processor will work with very low frequency. And you will not be able to start the next round until you finish the previous one. Back in the 60s, there was a trick with the conveyor processing, whereby processing of one instruction would be broken into pieces. Reading of the register and execution and so on. So, and after that, we shall start together with decoding. And we take one instruction, we take it from the memory, then decode and execute. But at the same time, without waiting for the end of processing, we select the next one. And this would be the main principle of the conveyor processes, just like you do the assembly of a car. That's when one car goes through a conveyor, but at the same time, many operations are being performed every several minutes, and that's how you can increase efficiency of your system, just by making each cycle that take less time, so arrange high frequency, and you perform instructions with overlapping, and in this way, on the whole, they will be done much faster. After explaining this first principle, I shall immediately switch to the presentation that will show the different cores of the company. And this presentation was made together with the Professor Charles Dutchik, the professor at the California Santa Cruz University in the Silicon Valley. Santa Cruz is located on the ocean shore, 1 hour drive from the Silicon Valley, but this department is exactly the evening department for the engineers who want to have higher to improve their skills, and so he has a special course for them for the chips, and he is going to give a workshop in Moscow Institute under the auspices of Rosnano. I can tell you what's this. If you wish, please approach me for more details for participation in that workshop. And in this short presentation, you will see several different processor cores, and I'll tell you how their structure depends on the market and how it what's in it for the Russian clients. One of the main reasons why I am here has to do with our company, along with the main revenue comes from Qualcomm, Acer, Broadcom, MediaTek. So all those companies license their cores and produce chips. And for Internet of Things, routers, Wi-Fi routers with embedded Linux. But lately, over the last five years, we got the first Russian clients in Zelenograd, like Elvis Neotech, who produces smart cameras, Baikal Electronics, making Baikal T1 processors that are used in the Russian Katyusha and digital equipment and controlling gas pipelines, controlling devices. Our cores are used by Progress company, who produces embedded chips. And we even have clients among small companies, like in Vladimir Lab Systems, that designs processors on 5150 core. But my main point is, for those cores to work well and to be successful in the global market, they need support of the software ecosystem, in particular of you, software engineers. Therefore, I want to briefly go around them, tell you what Russian clients use and what are the interesting features that are embedded and have to do to you as programmers. And through this ecosystem, you might ensure success of the Russian chips, both domestically and internationally. So, we have the classical MIPS conveyor at the start that is described in many textbooks like Hennessy, Patterson, Hennessy, and this conveyor is still used in some Russian projects, like in a Russian institute in the satellites for the space industry. So now our company has over a latest processor of the same class with a simple short conveyor that has better optimized timing. These processors are optimized for to minimize the size and the energy consumption, and with a low frequency, as energy consumption has to do. It is not growing in a linear way to frequency, but to the space or footprint. So these processors are used for the Internet of Things in the network with sensors, where processor has to use only one battery for years, wake up from time to time and send a message to a hub and then go to sleep again. So this core in particular would be used in Internet of Things. If I have another 5 minutes, I'll tell you about it. And then we have a core with over more conveyor stages, so it does less in one round. But with higher frequency. For instance, if your energy consumption budget is higher and you want to increase the frequency, you can use this core. And you see the principle here and understand why all the cores do not boil down. Why the whole world will not just select one specific core like ARM, Intel, or whatever, because when the producers of embedded system shop, they will find a certain balance. And then that's the slide that is showing this typical chart. When we maximize the smaller cores, so minimizing by the footprint or productivity, and the mid-level is they have important place in the market. They have high efficiency and reasonable energy consumption, like this processor that I'm involved in designing. And you can use these processors to build systems for performing tasks, and they can nomadic tasks. So, and this is an interactive process, that is used in chips from MediaTek and Qualcomm, and they built Linux computers for $5, like Mega Onion, used by the Russian company hypervisors for the hub and Internet of Things. A hub is a computer that will receive data from the sensors, and the very interesting special feature about this computer, of this processor, is that it has multi-threading on one core. This is an interesting trick. How many of you know how parallel interruption and context switching works in the software? Good. Then I tell you that hardware, the same process looks totally different. It supports multi-threading, unlike software. Hardware is totally different. So in the software, you have several threads in different parts of the memory. And you have, for instance, something from the timer, and you keep the current counter register, and then you just take and go back to the interruption, and you are in a different process. So it takes time, even if you optimize it very well. But again, switching in the hardware interruption in your processor, you have several copies of program counter and register of general purpose. After that, processor would sampling of instructions for some software counter, or even for several. And in the beginning of the conveyor, it will make queues with this selection, and then see what thread should go to the tail of the conveyor, where it will be executed. So it can actually switch the contact within one cycle, unlike hundreds of cycles in the most optimized software process. Why do we need that? It will address a very interesting purpose. It will serve a purpose. So the speed of activity of arithmetic operations was growing much faster than the memory access speed. So even having cache, you can imagine, in the early 80s, the processors on the first PC didn't even have the cache. But then caches were invented to address this issue, but it did not really solve the problem. And now, within one access to memory during cache, you can actually perform hundreds of arithmetic instructions. So therefore, the software will wait 50% of the time that need to turn to use the memory. And this hardware supported multi-threading is made in such a way that when a thread or process is waiting for this transaction from cache, the processor may just push it out from the tail and start processing the other thread. Without this tool, the processor of middle class like RM or MIPS, MIPS would ARM A9 will idle, will wait for 50% of their time for that task. And this thing allows you to load the processor without using the second core for the double core system. And the price of such trick is just 20% compared to the general hardware volume. And though you save on the footprint, that is proportional to the energy consumption. So now, in the processor that I6500, and the previous version, this is a super processor with multi-threading and several conveyors and finally, there are processors MIPS I5600 that are used as a core in the Russian Baikal processor. SMT with vector processing is one of them. ARM Neon, one of our processors, MIPS I5600, is an opportunity for one team immediately to perform arithmetics with many numbers. And the microprocessors presently follow up on the supercomputer trends in the late 60s. If you remember Cray cybercomputers, then the next area is programming of multi-core systems. So again, I have no time to describe it, but instead I'll talk about the very interesting trick that you can use if you want to go from software programming to software development to the hardware. Who knows about the logical integral scheme? You can. Our company has educational training programs and provide licenses for the low-end core, like MIPS Microactive UP, that is subsampling of that is within 5150 range, and you can use this code to synthesize your own system on Crystal. This package is free, and it can be used on a simple, cheap student's board, and it has an option. This core has an option of additional block where you can make your own instructions. So, for instance, you can make automatic arithmetic instructions and see how they influence, how it changes the time of execution. And they move together with the main conveyor. The conveyor does not wait until it executes. And the exception, this instruction will be killed, but interfaces were very simple. You can play with it, and a group in Singapore built a multi-core system, adding additional commands like send and receive and into this custom block, and built this matrix. So you can you can perform interesting tests. And within the next couple of minutes, I'll show you the slides from our Russian clients, in particular from Elvis Neotech, so for you to understand what's behind it. What? For the success of such projects, we need your support. So Elvis Neotech has a chance. We need to go to customers. Elvis Neotech is a company in Zelenograd, and used to be during the Soviet times, used to make onboard computers for the satellite station. One of them is the computer Silicon Valley Museum. So then they started to produce chips for satellites, including their digital signal processor and their own MIPS. And now they use mid-range and high-end cores for smart cameras that can do video compression and schematic analysis. So for instance, see that someone is trying to break into a warehouse or filter and transfer information. If they see a tree, they will just write it's a tree, or if they see a face, they will say it's a face. They have special blocks for video processing that indeed are very competitive globally, but for such projects to work well, the software ecosystem needs to support them. This is their Capri chip that's now is being launched. So it's 28 nanometers. So many other clients use the factories in Southeast Asia, in Taiwan, to produce something like that. And these 28 nanometers.
And this is one of the most advanced technologies for chips. And so PlayStation use the chips not so powerful. And this is the typical so workhorse. And so their chip has this very complicated design. It has a graphic processor and blocks, components made in Zelenograd, and so this we designed it at our office. This one is was designed in the United Kingdom, and some of them are made in Oregon. And it's true, it's an international project, truly international project. And so that's what it looks like. It's a blow-up diagram, and so that's the way it is located on a piece of crystal application processor. So because I've been working in Silicon Valley for 25 years, and I've never been to Russia. So ever since I moved to the States for 25 years, or in Soviet times, I participated in the design and development of Russian supercomputers. When I came to Russia 20 years later, so many thought that it was not possible, but 5 years later, so they became reality. So now just we have something that actually allowed us to market internationally, including with your support. And so they are. So we do this evaluation board right now, and the video cameras that they use for different things, and this is something that like Baikal Electronics and some other things Russian support. And it would be great if I could study more in Russia and study the course, downloading from our website, and study the adjacent areas and contribute to the development of this effort in Russia and internationally. Thank you very much.
Я так слышу, но это буквально на уровне слухов, и вот вы подтвердили.
Yeah, there is rumor or refuted or support that for each instant of use for your course, we have to get the approval from the government of the United States. So since we're a British company, so our rules are different from American companies' rules. So Department of State needs to give an approval. And I work at the business unit. Most of it is located in Santa Clara, California, which is Silicon Valley. And I go to lunch every day to the office of Intel, next to the office of Intel. So this is an interesting subject, and we had to go through it as a company. And then the Chinese companies had to go through it as well. So it's not done directly through the Department of State. Although so there's a company that is referred to as Bureau of Industry and Security that so then it controls us. And so then the blacklists they provide, you need to get an export license to do that. This is a normal process, so I can explain. So whether we need an approval of the Department of State. So 5 years ago, it would have been very difficult to do that, and the lawyers had to participate in that. But now it can be done. So this problem has been addressed. Our management in the UK found a way. Yes, to cooperate with Neotech, which is a Russian company, and that gives that does it all so without any hurdles and barriers, without any catastrophic difficulties. And so other companies face the same issue, as Synopsys, Cadence, Arc, but all these companies. So Russia is a hot market. And so 10 years ago, then the former VPSS thought that so in Russia nothing would happen for the next 20 years. That's what they thought. And then there was a lot of movement in Russia started recently, and then Russia became an interesting country of the second league. And now Russia is considered a country which is right after China. So very hot market, and that became possible due to those projects. And so in the last 5 years, a great deal of change has taken place. This revolution has occurred, and so now much depends on you to what extent this revolution will succeed. Because Russia is very seriously underrepresented in the global chip market, because they manufacture 0.4% of chips globally, and we need to increase it at least 10 times, because Russian engineers have a great deal of edge compared to Chinese engineers. So because Russian engineers are more independent, so they're ready to do homework, and so there is room in the market. And this is not normal that very few projects of the Russian origin are in that market. We need to change that. So our southern, so we purchased the board Xilinx, and so we promised now that we were not going to use it for the defense purposes in Crimea, and we bought it. Okay.